SSD project regarding the vulnerability fix and the auth OpenID functionality add. We got our MERN stack project that we did in the ITP assignment. In here, we fixed our vulnerabilities using OSAP SAP tool and the SonarQube tool that check both dynamic and the static vulnerabilities. Let's move on to the our fixed vulnerabilities. I have fixed the insecure random number generator for reference ID vulnerability. In here, there's a random number generator using math.random. Instead of that, I used UUID to generate that the others can't predict, and the security sensitive purpose due to predictable output. Instead of that, I have used UUID generator to create strong, unique, and the unpredictable IDs. Also, I have implemented the Open ID or auth. In here, there's a user can use their email to the login. Then if the already logged user, they can log into the system and see their details in here. Also, I can show using another Gmail to that. There's also is already logged user, so he or she can see their details, all the things. Let's say we have new user that's already not logged into the system. So in here we can track that using the Open ID. So that's why it's asking to give the continue. He is not already logged into the system. So I have implemented those both Open ID and OAuth successfully in the system. I hand over this to Oshan to continue.
My name is Gopal. I'll briefly cover two critical vulnerabilities I found. Code injection RC via well and regular expressions denial of service. Then I'll explain the fixes and why they're effective. First, uh, code injection RC that previously used eval to evaluate field names values at runtime. Eval execute arbitrary JavaScript strings, which lets an attacker to run malicious code on the client or server. So full remote code execution is the risk. Impact data theft, session takeover, system compromise. So as a fix, I removed eval entirely and introduced field values objects that maps field names to their values and used field values for access. This eliminates dynamic code execution, preserves validation logic, improves readability and performance, and closes the injection vector. Second, those attack this complex regular expressions with nested confess. For example, aggressive alphanumeric email regresses can trigger catastrophic backtracking. A crafted input causes exponential evaluation time, freezing the server browser. With concurrent requests, this becomes a server outage. So as a fix, replace vulnerable regresses with a linear character by character validation function. For example, validate with simple string checks and validate passport IDs by scanning each character. So this removes backtracking risk and easier to maintain reason about. Yeah, uh, that's about my vulnerabilities. Next, I'll hand over this to Shehan.
Um, I'm Hansaji KWS, and my IT number is IT 22335500. Uh, in this assignment, I was responsible for identifying and fixing two critical vulnerabilities in our system. The vulnerabilities I worked on were a missing anti-click checking header and the insecure random number generator in file naming. And also, I used security testing tools along with the SonarQube and SAP to detect these issues. First, let's talk about the missing anti-click checking header. When I tested the application, I found the HTTP responses did not include the X-frame options or content security policy, um, and also frame and sectors headers. Without these headers, an attacker could embed our application inside the hidden iframe on malicious site. This technique called clickjacking tricks users into clickjacking on elements they can't see, such as submitting buttons or settings, leading to unauthorized actions. Uh, to fix this, I added the content security policy frame and sectors self header, which prevent external sites from embedding our pages. For older browser support, I also added Xframe options deny. After testing, I confirmed that the application can no longer be loaded inside external iframes effectively, blocking click checking attempts. Uh, this is the second vulnerability I found. Insecure random number generator in file naming. Uh, Originally, the system used mathrandom function combined with the timestamp to generate unique file names. SonarQube flagged this with rule JavaScript because of mathrandom is not cryptographically secure and can be predictable. This made these file names vulnerable to guessing, which could lead to file overwrite attacks, denial of service issues, or even fraud of financial system. Uh, So the to fix this, I replaced mathrandom with Node.js crypto random bytes, which generate secure, unpredictable values. Uh, Now each uploaded file name includes both timestamp and cryptographically secure random string. This ensures uniqueness, unpredictability, and prevents attackers from predicting over files. In conclusion, by adding the proper anti-click checking and headers and using secure random generator for file naming, I significantly reduced this risk of click checking attacks, file tampering, or fraud. This fixes strength or the overall security of the application and ensure that the sensitive financial operations are protected. Next, I hand over this to Masha. Thank you.
I am Imogen Nirmale. My ID number is 22331618. I was responsible for identifying and fixing two critical security vulnerabilities. And the vulnerabilities I worked on were a cross-domain misconfiguration and incomplete content security policy. First, let's talk about cross misconfiguration. Cross-origin resource sharing. It is a mechanism that controls how web pages from one domain can interact with resources from another domain. Our application's backend API was configured an overlay permissive course policy. It used a wildcard, meaning it allowed requests from any external domain. This was a major risk because a malicious website could silently make requests to our application on behalf of a logged in user, potentially leading to a data theft or unauthorized actions. To fix this, we replace the permissive wildcard with a strict whitelist of allowed origins. Now the API only accepts requests from our specific front-end domains. This ensures that only trusted sources can communicate with our backend. Um, let's talk about second vulnerability. Incomplete Content Security Policy. CSP is a critical security header that acts as a whitelist, telling the browser which sources of scripts, styles, and other resources are allowed to load. Our application either lacked a strong CSP or had one missing key directives. This left us vulnerable to attack like cross-site scripting, where an attacker could inject malicious scripts into our web pages. To resolve this, we implement the Helmet.js middleware, which automatically sets secure headers, including a robust CSP. We define a strict policy that by default only allows resources to load it from our own domain, blocking any unauthorized external content. Thank you.